SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of Thermal Engineering Basic and Applied, and in today's class we shall solve one numerical problem on flow nozzle. We have discussed about the efficiency of the nozzle, knowing the flow physics when a stream is flowing through a channel having convergent divergent shape. So, we have discussed that nozzle efficiency is influenced by a few factors. Those are friction, velocity of steam, and finally, the length of the nozzle. Importantly, friction plays an important role on the efficiency of the flow nozzle, but we have also seen that velocity of steam as well as the length of the nozzle indirectly affects the efficiency. So, this is the problem statement. Let us first read the problem statement, then we shall move to solve this. It is written, steam at 20 bar and 300 degree Celsius is allowed to expand through a nozzle up to 2 bar. What is the type of nozzle required? So, this is the first part of this problem. That means, inlet pressure is given, inlet temperature is given, and also exit pressure is given. You may recall in the last class when we have talked about the nozzle efficiency, identifying several factors those affect the nozzle efficiency. We have discussed that inlet pressure is fixed, outlet pressure is also fixed, and if the process is isentropic, then exit velocity is also fixed. So, inlet conditions are given, that is pressure and temperature, outlet pressure is given, that is 2 bar, and from there we need to know which type of nozzle is needed for the operation, I mean of course, the steam power cycle. The next part of the problem is find the exit velocity and area for a nozzle efficiency of 0.9. So, basically it is given that the nozzle efficiency is 90%. For that, what would be the exit velocity, and mass flow rate of steam is 2 kg per second. Assume that loss in the convergent portion of the nozzle is negligible. You know that this line, if we underline this particular line, probably this line is giving us a clue about the type of the nozzle. So, it is given that the loss in the convergent portion of the nozzle is negligible. So, if the nozzle is purely convergent type, then perhaps it is an indication, but since we really cannot trivially ignore the frictional loss, so frictional losses to be precise, so perhaps it is not a purely convergent type. So, this is giving us a clue, but let us look at the actual case. So, if we start writing, rather if we start solving this problem, so we really do not know. First of all, we need to understand which type of nozzle it is. So, it is given P1, that is 20 bar, T1 300 degree Celsius, those are the inlet condition, and P2 equal to 2 bar. So, this is the outlet condition. Now, when we have discussed about the critical pressure and also we have discussed that when a nozzle is said to be choked, that time we have discussed about the significance, physical significance of the critical pressure ratio or critical pressure to be precise. Now, say if we try to find out what is the critical pressure for this, for that we need to know what would be the index of expansion of the stream following the isentropic expansion. You know the value of index of expansion for the ideal gases is constant, but this is not a case for the steam. For steam, the index of expansion varies depending on the quality of steam at the inlet to the nozzle. So, let us now look at what would be the value of K for different cases of steam, that is for different inlet qualities of steam. So, if the quality of steam is inlet superheated, so I would like to write here the value of K, that is the index of expansion and this is the quality of steam. If the quality is superheated, superheated steam, the value is 1.3. So, you can assume when you are solving any numerical problem, you can assume that K should be 1.3 for steam if the quality of steam at the inlet to the nozzle is superheated. If the steam quality is dry saturated, it is 1.135. So, if the steam is dry saturated at the inlet to the nozzle, that is 1.135, and finally, if the steam is wet steam. So, these three are the different possibilities of steam that we may have at the inlet to the at the inlet of the nozzle. Either it may be superheated steam, it may be dry saturated, or it may be wet steam. If it is wet steam, then it is 1.0135 plus 0.1 into x. This x is the dryness fraction. So, we know what is dryness fraction of steam. So, if the steam is wet at the inlet of the nozzle, then perhaps we know what is the dryness fraction. From there we can calculate K. So, these are very important. Now, let us discuss about something on the critical pressure ratio, because by knowing the critical pressure ratio only we can say what type of nozzle is needed for the operation of steam power plant, where this type of nozzles are there. So, what we can do next? We can calculate critical pressure ratio. So, critical pressure ratio RC, that is P2 by P1 equal to, we know the formula 2 by K plus 1 power K by K minus 1. So, that is what we have derived, right. So, when we have talked about mass flow rate per unit area at the exit of the nozzle, from there we could establish the expression of critical pressure ratio. Now, if we use the value of K equal to 1.3, because if we go back to the problem statement, nothing is given. So, see, you can calculate what is the quality of steam at the inlet to the nozzle. So, it is given pressure and temperature. So, we have studied in thermodynamics from steam table, knowing these two properties we can assess the inlet quality of steam, that is the quality of steam at the inlet of the nozzle. So, knowing the value of pressure and temperature which is there, which the steam is having at the inlet of the nozzle, we can calculate what should be the, what is the state, whether the quality is 1 or it is less than 1. So, from there we can assess about the quality of steam. So, now if we, for this particular case I am telling from steam table, if you look at, the quality of steam is superheated. So, I can write from the inlet condition, inlet condition 20 bar, what you can assume, the inlet condition is steam is superheated. Okay. So, that is K equal to 1, then RC equal to P2 by P1 equal to 2 by 1.3 plus 1 power 1.3 minus 1.3 divided by 0.3. And if we do this calculation, you will be getting RC equal to P2 by P1 equal to 0.5457. What we can assume, what we can see from this particular expression is that the P2, that is the pressure. Now, this is the critical pressure, right. So, if we assume that the nozzle is having critical pressure and then that critical pressure P2. So, here let me write over here P1. So, if we go back to the previous slide, here we should not write P2 because this P2 is not the pressure at the exit. So, let us write this is P3 or it is write P exit, it is better to write. I had written it P2 because we did not know whether this is the pressure at the exit or it is critical pressure. So, let us write it is P exit and P2 is the exit pressure. So, P1 is the inlet pressure and P2 is the critical pressure. And P3 equal to P exit equal to exit pressure. So, we are assuming these three. So, what we can see, you know, that exit pressure is 2 bar, right, that is given. So, P exit comma 3 or 3. So, this exit pressure is 2 bar. What we can understand that P2, therefore, P2 equal to 0.5457 into 20 bar, which is greater than P exit or P3. So, the critical pressure is greater than the exit pressure. Then I had written in one of the previous classes that if the critical pressure is, so this is why this critical pressure is so important. The magnitude of critical pressure is greater than the exit pressure and hence the nozzle should be of convergent and convergent divergent type. So, I am writing since P critical or P2 is greater than P exit or P3, nozzle should be of convergent divergent type. So, this is very important to know. So, nozzle should be of convergent divergent type. So, this is the answer of for the first part of the question. So, this is convergent divergent type. Okay. So, now you have understood that the nozzle is of convergent divergent type. So, now let us look at the HS diagram and try to map the expansion process therein. So, if we go for the HS plane, say if we plot it, so this is the HS plane, right, and so this is right, and say this is the, so this is P critical equal to P 2, this is P 1 and this is P exit or P 3. If we take one point over here, say this is the point 1 and this is isentropic process. So, this is 3, this is 2, right. What we have discussed in the last class, that this is the isentropic process, but in real application it is very difficult to have or achieve isentropic process. So, accounting for the frictional losses, the process will deviate from the isentropic process and the actual process would be like this. So, actual process would be, for that we need to go back to the problem statement, the last line what it is written that the loss in the convergent portion in the nozzle is negligible. So, this statement is giving us a clue, as I have already told that this is not a purely convergent type of nozzle, but what we need to do, we need to assume that the loss due to frictional effect is negligible in the convergent part of the nozzle. If that is the case, then if I try to draw the actual process, it will look like this. So, this is 3 prime. So, this is the actual process. So, this is actual process and 1 to 3 is the isentropic process. So, 1, 2, 3 is the isentropic process, whereas 1, 2, 3 prime is the actual process, right, fine. Then what we need to do? We need to calculate what would be the exit velocity and area for a nozzle efficiency is given 0.9 and mass flow rate 2 kg per second. So, let us now try to calculate. See, nozzle efficiency eta nozzle, that is H 1 minus H 3 prime divided by H 1 minus H 3. So, this is what we have derived in the last class. So, this is nothing but the actual heat drop to the isentropic heat drop. So, this also can be related to the actual gain in kinetic energy that due to isentropic process. So, this is the case. Now, from steam table we can calculate what would be H 1, because we know the inlet conditions, that is pressure and temperature is given. So, what we need to know? We need to know H 3 prime. So, we need to know the H 3 prime from this expression. So, we can write H 3 prime will be equal to H 1 minus eta nozzle into H 1 minus H 3. Here H 1 we can calculate from steam table, H 3 we also can calculate from steam table, because if we can calculate entropy at point 1, entropy at point 3 is also equal and we know the exit pressure. So, knowing to these two properties, we also can calculate enthalpy from the steam table. So, let me tell you this H 1 equal 3022 kilojoule per kg and H3 that is 2588.8 kilojoule per kg. I am not going to tell you, but I have already mentioned by how we can calculate H1 and H3. Pressure is given 20 bar, temperature is given 300 degree Celsius inlet condition. From steam table we can get H1, pressure at exit is given, that is 2 bar, but the S3 is equal to S1 because process 1 and 3 is isentropic process. So, entropy at point 3 is equal to entropy at point 1. From inlet condition we can calculate entropy again from steam table, pressure and temperature, these two properties are given, and by calculating that entropy, so S3 equal to S1. So, knowing entropy at point 3 and pressure at point 3, that is P3, we can calculate S3 and that is what we have calculated. So, these two are let me write here from steam table. And process 1, 2, 3 is isentropic process. So, we have calculated. Now, if we plug in the value of H1 and H3 over here, and this is 0.9, then we can get H3 prime. So, H3 prime will be equal to 2632.12 kilojoule per kg. I am writing straight away the value of H3 prime. Okay. Now, next issue is what would be X3 prime. So, H3 prime equal to 2632.12 kilojoule per kg, P3 prime equal to P3, that is P exit equal to 2 bar. So, knowing these two properties and by looking at the Mollier diagram HS plane, we can get what is the quality dryness fraction. So, that is the beauty of the Mollier diagram, that we can straight away directly get the quality of steam. So, corresponding to this state, by looking at the Mollier diagram, we can find out what would be the dryness fraction at point 3 prime, and that is 0.955. Okay. So, if we go back to the previous slide and if we try to draw, so you know that what would be the dryness fraction line. So, this point 2, say we are drawing it. So, this is close to 1 and so this is x equal to 1. So, you can understand that point 3 prime is close to 1, that is not the saturated stream, but close to the saturated stream. Okay. So, that is given. Now, what next we need to do? See, exit pressure, that is 2 bar, and what we can calculate is, right. So, let me write here, right. So, P3 prime equal to P3 equal to 2 bar, okay. And we can calculate what would be Vg3 prime equal to Vg, right. So, that means at that particular condition what would be the specific volume of vapor. So, at that pressure what is specific volume of vapor? That is given 0.886 meter cube per kg. So, that means if we know the pressure P 3 that equal to 2 bar and that equal to 20 bar. So, we can calculate what is V g for that pressure. Now, that V g, so what would be the specific volume at 3 prime? That V g multiplied by the dryness fraction. So, try to understand, we have already calculated dryness fraction at point 3 prime, we know, and that point 3 prime is also on the P 3 line, that is exit pressure line. We have already calculated V g 3 prime equal to V g equal to 0.886. So, what would be V 3 prime, that is x 3 prime into V g or V g 3 prime, right. So, basically the specific volume of vapor at that pressure multiplied by the dryness fraction, that will give the specific volume of steam at that particular point, that is at the exit of the nozzle. So, this 3 prime is the actual state of steam at the nozzle exit, right. So, this is the case. Now, this is, if we calculate, we will be getting 0.955 into 0.886. So, that means 0.8416 meter cube per kg, right. So, this is the specific volume of steam at the exit of the nozzle we have calculated. So, let me tell you once again, specific volume of steam at that pressure that we can get from steam table. So, this is from steam table. Three prime is also located on the same pressure line. So, at that 3 prime we need to know the specific volume. So, that is nothing but dryness fraction of that particular point multiplied by the specific volume of steam when the steam quality is saturated steam. So, that is V g. So, we have calculated. Now, next we need to calculate what would be the exit velocity, of steam. So, this would be again actual exit velocity of steam. So, this is C 3 prime, that would be equal to, we have already calculated in the last class that what would be the exit velocity of steam if we ignore the velocity of steam at the inlet of the nozzle, assuming the fact that velocity of steam at the inlet of the nozzle is very small as compared to the velocity of steam at the exit of the nozzle, because our objective is to increase C 3 prime, and that is, if we recall that formula, that is nothing but 44.2 into under root delta H, that is H 1 minus H 3 prime. So, we have already calculated H 3 prime, and if we plug in the value, that is 44.2 under root 3022 minus 2632.12. So, that should be meter per second. So, unit should be meter per second. In fact, I also have discussed the unit conversion. So, if we calculate it, we are getting, this is 883.04 meter per second. So, can you imagine what is the exit velocity of steam at the, exit of the nozzle? So, this is meter per second. So, steam which will come out from the nozzle in the form of a jet, just like a bullet is coming out. So, that jet will now strike the turbine blade, and it is because of this momentum change, some momentum will be absorbed by the shaft of the turbine wheel. Now, if we know the exit velocity, then we can write what would be area. So, exit area say exit area is A3 prime and it is this A3 prime will be equal to V3 prime divided by C3 prime 2 into, right. So, if we go back to the problem statement, see why you are writing 2, because mass flow rate is given 2 kg per second, right. So, we are writing this expression from the fact that mass flow rate of steam, that is A3 prime into C3 prime divided by V3 prime, right. So, this is the mass flow rate of steam. Now, you have seen, so basically area into velocity into density, instead of writing density you have written the specific volume. So, this is very straightforward formula. So, this is mass flow rate of steam. And that is given 2 kg per second. So, I have written A3 prime equal to m dot s 2 into V3 prime divided by C3 prime. So, this is m dot s, and if we try to get it, the actual answer is, the answer of this particular problem is 19.1 centimeter square. So, this is the answer. So, let me tell you, if I mark this, so this is the area of the nozzle at its exit, this is the velocity of steam at the exit, and this is the type of the nozzle. So, these three are the solutions for this particular problem. So, if we try to summarize, we have taken one example. We have seen that from the given data how we can determine the type of a nozzle specific to that application. Then from the known data, using the formula that we have derived till now, we could find out the velocity at the exit of the nozzle, area of the nozzle for this particular convergent divergent type of nozzle. So, this is the last class of this module of this course. From next class onward, we shall discuss about steam turbine. Thank you.